last time we met, we had just discussed the Hardy-Weinberg equations and what those equations represent and how they can be used as a tool for us to determine if evolution is occurring when we see a significant deviation from the allele frequencies we would expect in the pattern that we would expect to see in those populations. And that once if we don't see a difference, there's no evolution occurring, and we're in Hardy-Weinberg equilibrium. If we do see a difference, a change in what we would expect, then we can say, okay, there is evidence of evolution occurring, and the Hardy-Weinberg assumptions are what lets us determine what is the force behind that evolution. So with these Hardy-Weinberg assumptions are all, we're assuming to be in equilibrium that none of these evolutionary forces are acting on our populations. So the first one on our list here is natural selection. Okay, for a Hardy-Weinberg, for a population to be in Hardy-Weinberg equilibrium, which means no evolution to occur, there must be no natural selection. Obviously, we've covered this one quite a bit to understand natural selection, what it is, and all that. So natural selection is the most common violation of the Hardy-Weinberg assumptions, therefore causing the most amount of evolution. So natural selection is a force that causes evolution, and therefore we leave Hardy-Weinberg equilibrium. Really quick, just to reiterate, right? These are different than the postulates of natural selection. The postulates of natural selection are conditions that must be met for natural selection to occur. These assumptions are all the ways that evolution can happen, and the Hardy-Weinberg assumptions are that these things are not in place. That's something that students sometimes miss on the test. They don't realize that you're looking for, oh, there's no evolution occurring, so, or there is evolution occurring, what postulate is, or sorry, what assumption is not being met here. So that's kind of something to keep in mind when you're comparing those two on the test, right? The natural selection postulates must be met for evolution to occur, and none of, and Hardy-Weinberg assumptions, right? And a violation of any of these assumptions might cause evolution to occur. So it's a little bit different in that setup. Whereas all these conditions must be met, or in this case, any one being violated would result in evolution occurring. All right, so natural selection, I won't go into that more because we've covered it a lot. Gene flow is when we have migration, right? That migration might be large groups leaving a population, or it might be large groups coming into a population. But as you can imagine, if we had, say, an allele that was 50% dominant and an allele that was 50% recessive in the population, right? Half the population had, or half the gene pool was one, half the gene pool was the other. In gene flow, then, we could have a population that was 75% yellow, and they're having large amounts migrate in to the population that we're studying, and that's going to be bringing in that dominant allele at a 75% rate rather than the 50% rate, and that's going to change our frequencies, right? That is a change in allele frequency over time. It's going to modify our population, and that's evolution. So large scale is the key for gene flow. Big movements, not small, big. And that's going to help us differentiate between gene flow and genetic drift. Genetic drift is when we have a small population that either survives or founds a new population. And because it's small, we can have wild shifts in our frequency. So let's imagine we have our 50-50, right? Setup like we were talking about. And let's say all but 100 individuals die off. Oh, well, let's change that. Let's say all but 20 individuals die off. And it just so happens, that means we have 40 alleles, right? 2 for each person, 20 individuals, 2 alleles for each person. That gets us to 40 alleles. Just by random chance, of those 40 alleles, instead of it being 50-50, maybe it was 55-45, right? It wasn't because that allele helped them survive better. Maybe it was just that a family that happened to have that allele were in the area where you were able to survive just by chance. That's one of the key things for genetic drift. It's random. different than natural selection in that way. And so because they're surviving by random chance and they just by random don't reflect the source population, right? That's why we needed to get down to 20 individuals. Out of those 20 individuals, 40 total alleles, we end up with 55 dominant, 45 recessive. Now we have a shift. That's evolution. Think about why we needed to be a small sample size, right? If we had 1,000 individuals that survived, the probability that out of 1,000 individuals, we'd have a big deviation from the source population gets pretty low, right? The more individuals we add in to our survival group, the less likely it is to deviate from the source population. So we need that small sample that survives or founds a new area to allow for that allele frequency shift to be more probable. So genetic drift is all about small populations surviving. Now, I just want to jump over to something really quick. Some of you may have been aware at some point of people using DNA studies to try and dispute the veracity of the Book of Mormon account that's told there. And maybe about 10 years ago or so, some professors and experts that are members of the church were approached and asked to write an essay addressing this topic because it was controversial for some people. And so they got together and they wrote this article. And I want you to notice right here, right, the founder effect and population bottleneck. And look at that right there, genetic drift. They actually are using their understanding of evolution to help us understand why there may not be significant DNA evidence that support the Book of Mormon account. And what they're saying here is that, we have, first of all, in the Book of Mormon account, an account of founder effect, right? A small population founding a new group, right? And so they're leaving Jerusalem and they're founding a new population. And essentially what the idea is, with such a small group leaving Jerusalem as part of that story, that small group may not reflect the allele frequencies, the genetic profile of the source population. And so that's one place where we could see significant genetic differences, right, just due to founder effect. And then we have in the Book of Mormon account significant accounts of bottleneck, right? And that's what this is showing here. We have all these different varieties in the DNA, but when there's a catastrophic event that kills off a large portion of the population, of which we have accounts of in the Book of Mormon, of course, we see that the genetic diversity becomes much, much lower. And by random chance, a lot of these different frequencies are eliminated. And we have a genetic drift event there again, and he's going through and explaining these concepts that we're talking about to help us understand that the Book of Mormon account has both founder effect and population bottlenecks that would have resulted in genetic drift and changes in the population. In addition to that, we have gene flow that is described in the Book of Mormon, right? Populations coming in from at different times there. We also are going to see if we're trying, well, what are we comparing the Native Americans to, where we're comparing them to Jewish populations that exist today? Well, there's been significant migration in Jewish populations throughout history, significant bottleneck effects in Jewish populations, and significant migrations. And so the idea that we would expect to, thousands of years after these groups were together, according to the Book of Mormon, that there would be genetic markers that would clearly target these two and we could detect those sequences easily, is denying how we understand that evolution works. And because of our understanding of how it works, we can understand why the evidence some might claim is not nearly as, it doesn't hold up to what we would expect to see. One thing that's important to point out too, and I mentioned this in the article, that even those that would try and say, oh, there is genetic evidence, and there has been a few things pointed out where there might be Jewish DNA found in a few Native American populations, um, that even that is kind of a tenuous claim at best too, because we don't know if when that migration would have come, right? The Jewish DNA we were founding, I believe it was Cherokee, if I remember correctly. I'm not 100% sure on that. But even those groups, we don't know when that would have come. So that is not exactly strong evidence for the claims of the Book of Mormon either. And the DNA is just probably not a good tool to test these claims. And so that's what it's saying here, I believe, in this section, right? Native Americans whose ancestors include Book of Mormon peoples may not be able to confirm their relationship using their DNA. So it's just not, because of these forces that we're aware of, not a great way of testing, as some people might think. Okay. Next is we must have random mating. There must be random mating to be in Hardy-Weinberg equilibrium. If one individual or group of individuals with a particular phenotype get to preferentially reproduce, they get to reproduce more, that's going to mean the next generation is going to look more like them. And as a result, that's a bad, that's going to be a change in the population and evolution occurring. And the last one is mutation. When we have mutations can cause recessive particular alleles to essentially reemerge. Non-functional alleles is typically how that happens. And so mutations, high mutation rates can reintroduce recessive alleles at frequencies that we don't anticipate or we wouldn't predict, and that would cause a shift in the population there too. So if you can imagine then, if we're trying to think of a population where none of these forces are acting upon it, that's going to be pretty rare, right? And it may not be acting on it for many traits, right? Like I don't think, I wouldn't say that human earlobe shape, whether it's attached or unattached, has any of these things acting upon. And so that particular characteristic may not be under evolution. But for example, HIV rates are very likely in Africa, causing a shift in allele frequency relating to the CD4 receptor on the surface of cells. If you have a certain mutation there, you actually are immune to HIV. And so that would be natural selection, for example, acting on the human population. So not only so we can think of Hardy-Weinberg as acting on particular genetic genetically derived phenotypes, and that for no evolution to be occurring, it would have to be in place for every single characteristic of the organism. And so this is why when we talk about teleology, this idea that organisms stopped evolving someplace along the path and everything else continued and it eventually becomes human-like. The idea that things stopped evolving is just wrong. That everything is that's in existence is very likely having at least one trait be put under evolutionary pressure from one of these mechanisms.